Hello, everyone. My name is Ty. Our group did an app called AirCrypto. My partners are Dao and Fee. And what is our app? So, what is AirCrypto? It is a Python CLI toolkit. It runs directly from the terminal, no GUI required. It can also encrypt messages and files, symmetric password and asymmetric key pair encryptions, signature and key management, so sign, verify, generate, and organize cryptography keys. And on the far right is what the app looks like when you first open it up in a terminal. What are some of the features for our app is symmetric encryption. So we have AES, GCM, password based for messaging and files. We have asymmetric encryption using the RSA 2048 for public/private key pair encryption. We have digital signatures for RSA and SHH, sorry, for just verifying files and keys. We have key management for generate, export, and importing cryptography keys. We also have a menu-based interface. No, it's a CLI, command line interface, and you navigate the app with number keys. Now I'm gonna bring it over to Dao.
Hello everyone, this is Dao Nguyen, and for the symmetric encryption and decryption process, we use the Advanced Encryption Standard with Galileo Counter Mode, otherwise known as AES-GCM. AES is a symmetric block cipher and has a variety of key lengths such as 128, 192, and 256 bits, and it also always works with 128-bit block sizes. GCM is a mode of operation that can be applied to the block ciphers, and this helps in resulting in confidentiality and the integrity of data. To put it as simply as possible, AES encrypts data in blocks. Counter mode allows blocks to be encrypted in parallel with the use of the initializing vectors and the counter. And then Galileo mode helps to create an authentication tag using a G hash. Another important part is additional authenticated data, which is data that is authenticated but not encrypted. For the encryption process, AES takes the key and the combination block of the counter and the initializing vector, or the nonce, and generates a key stream. Then the plain text is XORed with the key stream, and this process repeats until all blocks are encrypted. Then it's lined up together and put together, and it produces an authentication tag. For the decryption process, it reconstructs a key stream with a similar process to encryption, but instead of the plain text XORing with the key stream, it's a ciphertext. Then after it will reproduce a tag, and if the reproduced tag is the same, you get the correct plain text. If not, the decryption process fails, and you know that the file may have been tampered with. For key generation, we use script. Script is a password-based key derivation function, or KDF, and that's a cryptography tool to transform input to cryptographic keys, such as a password. It helps provide another layer of defense against certain attacks because it's more computationally expensive. It includes the salt, memory hardness, and sequential computation. And the parameters that you can specify are the cost parameters, which is CPU and memory costs, block size, and parallelization. For the asymmetric key generation, we used RSA 2048. It's the Breves Shamir Adelman private and public key pair. So the security of the RSA is based on difficulty in factoring a large number into two primes. And there's generally three processes that are included in RSA, which is the key generation of the public and private key, encryption, and decryption. RSA can also be used for digital signatures and certificates. We use the RSA OE padding, which is the optimal asymmetric encryption padding. It helps change the message before RSA encryption, and that results in the same input having a different ciphertext. It has the random seed, match generation, function, and the hash of an optional label. So we use hybrid encryption and decryption. So for the encryption, we grab the public key, get a user input, and then generate an AES 256 session key. Then you'll encrypt the message with AES GCM and encrypt the session key with the public key and RSA OA padding. Then you'll package all that information and we'll store it into a JSON file. And for the decryption process, you would grab the public key, open that package, and then decode information in the package, such as the key, nonce, and ciphertext, and then you will decrypt the AES session key with a private key. And then that will then help you to attempt to decrypt the encrypted message.
Okay, so for the final portion of AirCrypto, we implemented digital signatures. The purpose of digital signatures is to ensure data integrity. This means like even the smallest change in the data will result in like a completely different hash. It allows us to verify signatures using a public and private key pair. So instead of like verifying the person, our system verifies that the signature matches the corresponding key. This supports concepts like non-repudiation, meaning users cannot deny signing, but in our implementation, this is only partially true. Since we do not have an identity verification like a certificate authority, features include RSA 2048, key pair generation, alongside the ability to sign and verify both messages and files. Its design is based on asymmetric cryptography, where private keys are used to sign and public keys are used to verify. So, when we look at the signing and verification process, first the data is hashed using SHA-256, where it converts it into a fixed length digest. This ensures integrity since even small changes in the data produce a completely different hash. Next is the hash being signed using the private key with RSA PSS padding. This adds randomness, making signatures more secure and resistant to things like forgery attacks. And finally, for verification, the public key is used. The system recomputes the hash of the data and uses the public key to verify the signature. If verification is successful, the data is valid and unchanged. If it fails, the signature will be rejected. So when it comes to limitations in our implementation of AirCrypto, first are private keys being stored locally without encryption or secure storage, which is a security risk if systems are compromised, especially in the real world. Second is that there is no identity verification system or certificate authority, so there is actually no confirmation on who actually owns a key. Like mentioned before, AirCrypto only achieves partial non-repudiation since we can verify keys but not actual identities. Finally, we use static RSA keys, meaning there is no forward secrecy. So if a private key is compromised, previously signed data are at risk. So here are our sources we used when it came to developing AirCrypto. We used official standards like NIST and RFC documents alongside implementation guides to support our use of encryption, key derivation, and digital signatures.
Hello, everyone. This is the demo part of our presentation. This is AirCrypto, our app. So I'm going to show you how it works. So first, we need to generate a key. We press 1 to generate a key. And for this part, we're going to just do number 1 as well, a symmetric key. Key name is going to be test or class. And you see here, the key is saved in keys. Keys is right here on the far left. We have it right here. Now, if we go back and we encrypt something, let's encrypt a message. Passwords for now, it's going to be QWER, just for simple stuff. Message to encrypt. This is a test for class. We get this encrypted message with this long string, so all we have to do is just copy this string. We have it copied. And then we press enter to return to main menu. We hit back once, decrypt, message as 1, password is QWER, and we do the encrypted stuff, enter it, and this is a test for class. We can also encrypt a file. Path to file to encrypt is going to be over here into files, and we're just going to make a text document called hello.txt. And if you open it, we're going to type in this is also a test for class. And then we're just going to quickly save it. And then we're going to go back to the file explorer, click on it, right click, copy as path. Boom, password is QWER. Output file. Right now, we're going to leave it blank. We can put a path if we want it somewhere else, but we're just going to press enter, and it's going to pop up here. For right now, I don't know why on my computer says Wireshark, but it's a .enc file. Then we're just going to press enter, and hit back, decrypt, file, path to that .enc. It's going to be right here. We could just click on here, open with Notepad, and we can see that it's encrypted. So now if we do copy as path, paste it right here, password is QWER, output file, we're just going to leave blank, and it just decrypt it. And right here, we can see that the time is different. This one is more recent than this. So if we double click it, and it's back to this is also a test for class. Now we can do a generate key into a asymmetric key pair. We click on this, name for a key pair, test for class, and it makes a private and a public. So if you go back to keys, we have our public and private. So now if you go back, we can also export our public keys if we need to, or import another person's public key. But right now we're just going to go back to encrypt, asymmetric message, path to the public key. So right here, the pub.pem is our public key. Copy as path, right click, press enter, message to encrypt. This is another test for class. And we're going to leave it blank. This one will go here, called message.enc. So we press enter, and we go back one, we can decrypt message, asymmetric message. This is your private key. Remember, never share your private key with anyone, only your public. So now if you put this here, press enter, path to that ENC. So if you go back, this .enc, copy as path, right click, message is another test for class. This is our main premise of our app. This is also a sign/verify, but for this demo, to make it nice and short, we're not going to show off this sign/verified. But in here, we can sign something, and we can also verify that it's actually real and didn't get tampered with. So thank you for watching this demo.